webinar of the 2015-2016 year. This series this year begins with a couple of code introductions. We've had a couple of new codes donated to the repository in the last couple of years. That includes BurnMan, SW4, and Virtual Quake. Then in the winter, the series will take a total different turn, and we'll go do a series of talks on uncertainty and verification and validation. We actually have several leading experts in the field kicking us off in January who will introduce us to the topic, and this will be followed by several talks with applications to the earth sciences. So I urge everybody to log into, especially the first two webinars, to if you're unfamiliar with the topic. Okay, so today's webinar is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and the presenter will have their microphones enabled, so if you need anything, please use the chat window to type in your questions or to communicate with others. During the Q&A session at the end of the talk, if you like your mic enabled, please raise your hand and we'll do that. Okay, so today's webinar features a project initiated in 2012 during the CITER Summer Program in Santa Barbara, California, and has culminated in the open source mineral physics toolkit BurnMan. This project is a collaboration between 5 researchers spanning 8 time zones, all of which we're missing one here today. So from east to west, the collaborators are Bob Myhill, who couldn't be with us today. He's from the University of Bayreuth. Sanne, Cottar, sorry if I butcher names, by the way, University of Cambridge. Timo Heister from Clemson University, Cayman Unterborn from Ohio State University, and Ian Rose from the University of California, Berkeley. So without further ado, I'll turn the mic over to the team.
All right, thanks Lorraine, thanks for the introduction. And hi everyone, welcome to this introductory talk to BurnMan, the software BurnMan. My name is Timo Heister. I'll start the introduction, and we are dynamically switching back and forth between whoever managed to get their microphone to work. But yeah, so this is a group effort between Sanne, me, Bob, Ian, and KMan, as you can read on the title slide. Before I get started, please let me know if, I don't know, my voice cuts out or there's a question or something like that, because I don't hear a lot when I'm talking like this. And second thing, I would like to thank CIG for the support and for hosting BurnMan, for accepting it. And I would also like to thank CITER, the Cooperative Institute for Dynamic Earth and Research, and indirectly also NSF, because NSF is sponsoring CITER and CIG, so their support is greatly appreciated. All right, so let's get started. The talk today is A, an introduction to BurnMan, B, we go a bit into the details, C, we show some examples of research that each of us individually do using BurnMan, and then if we have time, we do a live demo. I'm not quite sure, but we'll see, and if it works, that is. All right, so let's get started. So BurnMan is a thermoelastic toolkit. It's written in Python. It is a library, as in it offers functionality that you can call and use in your own Python scripts. And it has a bunch of examples. It is open source. It's available on GitHub on the Geodynamics website, and you can also find it through the link on the first page. But if you Google for BurnMan, then yeah, still, if you Google for BurnMan and mental convection or mental toolkit, you'll find it. I want to stress this in the beginning, and I'll get back to this a couple of times. It is very modular. It is a library, so you can combine all the pieces in separate ways and do all kinds of interesting things with it. And so the goal is, if you look at the picture there on the right, which is a cut into Earth, and the goal is to compute properties of the minerals in the Earth or in whatever other planet you're interested in a self-consistent way. So the main idea is you provide minerals, and then we can find out all kinds of properties of the minerals depending on depth and other properties. Okay, so that's the high-level introduction. So let's go in it a little bit more. How did we come up working on this? Okay, so initially we started at CIDR in 2012, and if you don't know what CIDR or the CIDR summer programs are, you should better find out, because that's a really great summer program that's done every year. Anyway, so we met as a group there. You can see a picture down there of us working on it. And we actually had a different topic. Well, we had a scientific question we wanted to answer, namely, what is the magnesium silicate ratio of the lower mantle? Or is the lower mantle different than the upper mantle with respect to the mineral composition, basically? And we wanted to infer this and to find out if this is true or not by doing mineral physics computation and comparing that to seismic velocities that we can observe, because we don't know what's going on in the lower mantle otherwise. And so while we're doing this, we realized that's really difficult to compute these things and to compare to seismic velocities. And it's really difficult to reproduce results, do things consistently. And also, there are many people who try to solve these problems, and often they have their Excel spreadsheets and they make mistakes, or it's very difficult to use, or it's not flexible, and so on. And so very quickly, our focus switched from this scientific question there at the top to let's write a software that's useful for many people. And yeah, so that started in 2012. Yeah, and our hope is that this is used by the community and being contributed to, and yeah, helps the scientists. Okay, so how is the high-level workflow, or what can BurnMan do? You start with your minerals, and you want in a way, one thing where let me go back one slide, what we did here was the question, compare this to seismic velocities. So what we needed in this example is we start from a mineral and we go all the way to fake seismic velocities, so that we can compare, or we can create a fake seismic profile and then compare it to a real measurement profile. So you start with the composition. You use an equation of state to compute the thermoelastic parameters of the mineral, let's say, in a certain depth. And from that, you can, if you want, compare it with seismic velocities. So that's the very high-level overview. I have another picture that goes into a little bit more detail. Namely, you have to put in certain planetary conditions. So you have a geotherm that provides temperature, pressure profiles. You have your minerals that you need to put in. There's a mineral database included, but you might also add your own. And with that, you can compute the elastic properties with an equation of state that you also need. And then to combine minerals into a rock, you need to do the correct averaging of certain parameters and properties. And then you can compare to observed seismic velocities. We also have some of them already included. So that's the high-level overview, but everything here is modular. So you can plug and play at any point. You can plug in alternatives. You can write alternatives. You have always many different choices. And you can do forward modeling, look at errors, look at what the differences are, plot things, and so on and so on. So it's very flexible, even though it looks like here that there's just a flow from left to right. Yeah, it's modular anyway. All right, so that is the beginning. That's the overview. And here I would like to switch to KMan if we can figure this out.
Yeah, sure. Can you hear me, Timo?
Yeah.
Okay. So I'm going to go over a little bit about all of the different modules Timo mentioned and all of the things that are currently hard-coded, and I'll sort of stress at every level that you as a user can add your own variation on this if you want to test your own hypotheses or different equations of state, anything like that. So the first thing up is equation of state, and just for the non-mineral physicists, the equation of state is just a function that relates the density of a mineral to the pressure, temperature, composition of that, of whatever material you're looking at. Currently, BurnMan contains two isothermal equations of state, the Birch-Murnaghan, well, second and third order Birch-Murnaghan, modified Tate. And then it is also able to calculate thermal equations of state, so the isothermal equation of state plus a thermal pressure term. And we currently have three. Migruneisen Debye correction. We have the Stixrud and Lithgow-Bertoloni formulation of that, and Holland and Powell. And you can use any of these. You can try them with, well, yeah, you can use any of those equations of state, and you don't even have to use a full thermal. You can use an isothermal when running your models. And you can see in the plot over here, it's a little bit hard to see on my screen, it's a little small, but we've got a shear velocity versus pressure on the top and pressure versus density, and you can see sort of all the different equations of state and how those velocities and densities, oh, excellent, can vary between. And you can see in shear velocity particularly, you see quite a few bit of variation between the different equations of state, whereas in density you don't really. So that may be something you would consider when you're using this, when using BurnMan, which equation of state you'd like to use for whatever purpose you're using it for. Okay, let's zoom out. Oops. And okay, so in the bigger picture, those were just two parameters you can calculate, seismic velocity and density, but you can certainly, with BurnMan, run quite a few other things, or derive a few other properties, things like Gruneisen parameters, some thermodynamic properties, Gibbs energies, enthalpies, or down the list, density, of course, thermal expansivity, various bulk moduli, and specific heats. And these are all, currently BurnMan isn't written to solve these directly, but you as a user can add in modules to solve for those if you'd like. All right, let's go to the next. So another aspect of when solving these, if you're solving a thermal equation of state, you need something, you need a geotherm, something that tells you how temperature changes with either depth or pressure. And currently, we have a few hard-coded geotherms in the in BurnMan, but you can also write your own adiabat. You can have your own particular geotherm of choice that you can just hand write and put into BurnMan. You can read off of a table as well, and at every particular step of the modules that we showed in that flowchart, there's something you as a user can add in your own or use the default or whatever you'd like using BurnMan. Next up, we mentioned this earlier, the mineral library. I think we debated yesterday, and I think we came up, we have dozens of minerals in our library, not quite hundreds, but we do have quite a few spanning the upper and lower mantle. This one key here is that the exact parameters you will input depends on the equation of state that you're using. So we actually make you, BurnMan wants you to tell us the exact equation of state you're using, so it knows how to solve that equation. And I'll show in another slide what happens when you mix equations of state data with a different equation of state. You'll get wrong answers. It is very, very easy to add your own minerals, particularly if you have a set of data and you can use BurnMan to fit it to an equation of state, and then use those fits to calculate seismic profiles, things like that. And everything currently is in SI units, and that's just to make our lives easier as we put in all of these equations. All right. Another thing BurnMan is able to do is solid solutions, and we mentioned this earlier. When you have multiple minerals, you need to calculate the average of those minerals. So currently we have things like an ideal solution, asymmetric solutions, subregular solutions. I believe we might be adding a few more. But currently, if you would like to use this, you can certainly add in that level of complexity. And here's an example down here for magnesium iron perovskite. You can see we have it currently as in self.end members as a mixture of magnesium perovskite, iron perovskite, and aluminum perovskite. And you can, as a user, tell what are the molar fractions for those things, and it will self-consistently solve that rock for you. I think.
Can I take over here?
Yeah, go ahead.
Hi, everyone. So once we have the minerals and the solid solutions, you want to combine them into a mechanical mixture, and we often call this a rock within BurnMan. So here are some examples of what the script looks like when you're defining a composite. So the top example is a very simple example of mixing two types of minerals. In this case, it's 95% perovskite and 5% periclase. And so this is how you define it in BurnMan, as you call composite and you give it the amounts of perovskite and periclase, and then you give it the minerals that you're including. And these two minerals are taken from the Stixrud and the Berkeley 2011 library. Beneath that is an example where it's including solid solutions. So in this case, you want to preset the solid solution and mix in the magnesium perovskite, iron perovskite, and aluminum perovskite. This is done in the second line with 10% iron included. And then you mix in your solid solution and minerals, for example. In the next line, you can combine as many solid solution and minerals as you would like. And in this case, it's 80% of the perovskite solid solution with 20% periclase. And so from this mixture, you want to get, for example, the mobility and the wave speeds. And to do this, you need to average these minerals and solid solutions in some way. So to do this, BurnMan includes various averaging schemes. Here's some examples of what the geometries of the minerals would look like in these various averaging schemes. For example, the Voigt and the Rose are examples of having constant strain and having constant stress across the different minerals. So these are kind of upper bound and lower bound estimates of what kind of geometries you could have. Of course, the truth lies somewhere in between, and lots of people use the Voigt-Rose-Hill average, which is just the average between these two bounds. There's also a Hashing-Strickman bound included, which Ian included, which I think is under the assumption that one mineral is an inclusion in the other mineral. On the next slide, you can see the result of different mixtures between periclase and perovskite. In this case, this is not the most extreme example to show the differences between the different averaging schemes, as you might see. So the yellow line here is the perovskite and the green line is the periclase. And in the other colors, you see all the different averaging schemes that are included. And so with these variations, it does not make a huge difference. But if you combine more with more extreme velocity variations, you might get a different result. There's also a number of seismic models included in BurnMan. Here, currently, there's only 1D seismic models, but we hope to include 3D seismic models soon, so you can look and test different lateral velocity variations. Here are the current ones plotted out, and you can plot this yourself with one of the example scripts. And what we also have in BurnMan is that you can easily ask for the modelling of the seismic models in case you want to compare that and look more from a mineral physical point of view. I think we're trying to keep all the applications as easy as possible for both mineral physicists and seismologists to use. Similarly, as to all the mineral physical parameters, these are all given in SI units. Only for plotting here, I converted them to kilometers per second, for example, instead of meters per second. And as been mentioned several times before, it's all very modular. All these different, these are all different models of different classes for the equation of states, the minerals, the solid solution model, geotherms. Any of these, if you don't like what is included now, you can easily include your own. The way I usually do it is to copy the format of the model or the class as it is included, and then fill in my own functions for all the different compensations that I might want to do, and my own parameters for the minerals. And we would very much like to see new additions, and you're very welcome to commit those to the code through GitHub. So that was a quick overview of part of the code, and we'll now show some examples of the applications. I guess we're back to Cayman.
Cayman, before you get started, just want to add two things. So first thing is, if I go back here, if you look at the slides later on, you'll see that we have the Python file name next to it. All the tools that it's all included in BurnMan. These are all examples that generate these plots. So if you want to go back, there's no magic there and so on. So you can look at them and modify them and so on. I also posted a link to the PDF in the chat down there. And now, if we go on to something more, before we go on to something more complicated, if there are questions now, let us know. Yes. Otherwise, I would go to Cayman now.
Yeah, no problem. So looking at examples, as Timo mentioned, all of the examples we're showing are things we include in the BurnMan you would download through CIG, and you can run them on your own machine and see how they work, understand them, and they're meant to build on each other to really understand how BurnMan works, what its functionality is. So first up is just a very simple example script of sort of running BurnMan top to bottom, so this is, we chose some composition and a geotherm very simply, and this is an example beginner, and then this is what would pop out. This plot, or these 4 plots would pop out, and it can show you very easily. The blue curve is the computational S speed, P speed, density, and along some geotherm in the red, and you can very quickly compare your choice of composition and geotherm to PREM. In this case, the reference is PREM in the black, and you can see, so a very quick tool to just understand what are the implications of this mineral I've just measured, or I want to see what happens when I change the composition of the mantle by X. So after that, and here's the actual, this is it. This is the script to actually run example beginner. First, you import everything you need. Next up is you define your rock as some composite of, let's see, 0.8 and 0.2 of magnesium perovskite bridgemanite and magnesium oxide periclase. You choose your seismic model with which you would like to compare. You choose the depths over which you want to look at. You can also use pressures if you would like. And then in this next line, you actually solve for the seismic models. Next up, you choose your temperature. And in this very last line here, density, VP, VS, V5, this is all you need to call to run all of BurnMan given those choice of minerals, temperatures, and it will calculate for you including all of the averaging for a rock that is made of 80% bridgemanite and 20% periclase at these depths given some temperature. And that's the absolute easiest possible script you can use to run BurnMan from start to finish. It doesn't include the plotting aspect, but that's not too many more lines. Next up is something I mentioned earlier, which is reproducibility. And this is one of the things we quickly learned with BurnMan was the need to be self-consistent with not only our choice of equation of state, but which the data we use and how they were derived, what equation of state they were used to derive those data. And so I'm going to zoom in a little bit more on this figure to sort of show you. So this is shear velocity versus pressure. So the solid lines are correct fits to the data in blue. And you can see that running BurnMan with the correct fit data, so blue would be running a third order equation of state with third order data, whereas the dashed blue line would be running a third order fit into a second order equation, and vice versa. And you can see that by mixing data and equation of state, you can get drastically wrong answers. So it's something to note, which is why we include a fitting package so that you know you're doing an apples to apples comparison from your equation of state into BurnMan. So, and I will hand it back over to Sanne, I believe, for the next slide.
So this is a second example, and the goal of this example is to do a simple parameter search over the amount of perovskite that might be in the lower mantle, and here we can compare the resulting velocities from BurnMan to the velocities from PREM. And the resulting figure from the example is shown here. And as a function of percent perovskite, I'm showing the error for different seismic velocities, for density, for different modeling. You can see depending on which one you choose to fit, you might get a very different result. So you might find a nice fit when you try to decrease the error for the shear wave velocities, but that might not at the same time be the best fit for density or for the shear modulus at the same time. Obviously, this might be due to my choice of composition that I'm using here. I'm only searching over one parameter. One could add a lot more parameters like the amount of iron or the temperature in the lower mantle. But here we're just searching over one. Let's go to the next slide. So this is the code that does this. At the top of the code, you can see the import of the various libraries that are used. So NumPy is a general Python library that's just used for various computations. Computational functions are used in the code, or arrays, working with arrays. Then there's the input of matplotlib. This is for the plotting, which I'm actually not showing on the slide. It is cut off at the bottom, so you won't see it used here. And then BurnMan is imported, and the minerals library are imported. And at the top, we're loading PREM as reference. We're choosing a number of points to evaluate at, and there on the third line, we're using NumPy to select, to create an array of depths between 700 and 2800 kilometers. You can see this is again in meters here, everything is in SI units. And then we evaluate PREM at these specific depths, and we ask PREM to return pressure and density, P wave velocity, shear wave velocity, bulk sound velocity, and the bulk modulus and shear modulus. And we rename those size P, size rho, etc. in that line. I don't actually know if I have a pointer here, but in the next line we define the geotherm, and here is the Brownish-Shanklin geotherm. And we define the solid solutions that we're using in this case, so we're fixing these and not varying them in our source search. We're using those from the Stixrud and Bertoloni library, so again, MGFE perovskite, which we set having 6%. No, I don't think I'm controlling it very well. Okay, I'll turn that off. I'm not sure how to control the pointer. So we set the composition of the perovskite with 6% iron including, and then ferropericlase with 20% iron in this case. And then we define a function which is material error, which depends on the amount of perovskite. So at this point we start to define our composite, which depends on the amount of perovskite, and is the mixture between perovskite and ferropericlase, and we call this rock. And then we calculate the seismic velocities for the rock. So the equation of state that will be used in these calculations is inherent to the minerals. It's one of the mineral parameters, so it's fixed in this case. So we won't be using the wrong equation of state. And in this process, in this line, when I call velocities from rock, I can define the averaging scheme that will be used. In this case, it's Voigt-Rosehill. Voigt-Rosehill is also the default averaging scheme. So if you won't give it an averaging scheme here, that's the one that will be used. And this outputs the seismic velocities in the model that we want to compare. The next two lines are to print some lines out to your screen, so while it's running, you can actually watch it run, you know it's doing something. And then we calculate the errors by comparing, this is the L2 norm, comparing the output of the velocities from the rock to the velocities of PREM. And actually, the last couple lines is where a lot of it happens, because this is where we compute an array between 0 and 1 of the fractions. We take 40 different samples, and then in the last line, it actually runs through this array. So for x and xx, it calculates the material error, and it puts all the error output from material error into an array. So in the end, you have a 2D array of all different errors for the velocities in the anomaly and in one direction and the fractions in the other direction. And so I cut out the part that is actually plotting these errors. You could expand the last line into a couple lines where you're actually going through a for loop and calculating the errors for each of these and then plotting them. So those are examples that are included in the code and you can look at and you can run yourself, and there's many, many more. So BurnMan is a scripting tool. There's no direct user interface, but we do provide lots of examples where you can pick one and maybe modify it for your own applications. We want to show some examples here of how we're applying BurnMan for our own research projects. So these are not necessarily examples that are included in the code at this point. So I use BurnMan from a seismological point of view. So in part of my other research, I'm looking at pressure to shear wave conversions, which are shown in the little cartoon in the left. So when a pressure wave hits a seismic discontinuity in the mass transition zone, part of the energy will convert to a shear wave, and these arrive at the station roughly 40 to 70 seconds after the direct pressure wave. And so you can study these to look at the depth of the mantle transitions that cause these seismic discontinuity jumps. And so one of the questions I asked is if I could see a certain feature that is predicted for within cold slabs, which is shown in the cartoon on the right, where outside of the slabs you have a regular 660 where ringwoodite falls apart into periclase and perovskite. And within the slab, you have a kind of double transition where ringwoodite first turns into echinoderite and periclase, and then the echinoderite converts to perovskite beneath that. And so I used BurnMan to predict the velocity and the density jumps that are happening at these transitions to see if I could actually see these in my P2S conversions. And so on the left here, you see the little bit of script that I used to define this. So I define my perovskite, my echinoderite, my ringwoodite, and my periclase, and then I combine those into different rocks that represent the rocks in the mantle transition zone and in the lower mantle. These are all quite simple compositions and not necessarily fully realistic, but they are a good test to see if I can see this seismically. So I set the jumps here at brute force. These are not like calculations of where these minerals are stable or something. The depth at which the transitions happen are guided by what I see in my actual data. So on the right, you see the resulting shear wave velocities at the top for scenario 1, where there's one transition from ringwoodite to perovskite, and scenario 2, where there's echinoderite present in between. And you can already see from the jump here that the ringwoodite to echinoderite transition is quite weak. And so I use the velocity and the density profiles as input to seismic synthetic code that creates the waveforms, and from there I can look at these P2S conversions. And at the bottom, you can see synthetics for these two cases. You can see the difference in depth in the 660. It's actually quite tricky to see those double transitions, and with the quality of real data, it would be really hard to see the difference between these, at least at the frequencies that I'm using here. That's my example. So this is where Ian was going to speak.
Do we just want to skip Ian stuff, or we can? Yeah, mine kind of. So I'll talk about my research. Oh, go ahead, Timo.
Yeah, I think we can talk a little bit about it. So what Ian is trying to do is, he's actually writing. So it's about the generation of reference models for use in mantle convection simulations. So in this picture here, he's trying to show that you have 3 different things that kind of depend on each other that you don't know about a planet, right? So density and pressure and the gravity itself depend on each other. I assume that's what the G stands for. And what he wants to build is a self-consistent model based on a mineral setup, basically. And so this is an example here where he puts in a rock and he computes whatever looking like internal structure of Mercury using that. I'm not sure. Is that example already part of BurnMan? I think one of the versions is. Yeah.
I think it is. Yeah. The planet.
Build a planet is the example here. Okay. If you want to know more, you can talk to Ian. KMan? No.
Oh. I'll do it. Thanks, Timo. So I'm sort of building on Ian's reference planet model, whereas I'm looking at solving for interior structure of exoplanets. So with exoplanets, we only have two current observables, the planet's mass and its radius. So from those two data points, and thus the average density of the planet, we have to infer all of the interior structure. So what we wanted to know, our first question was, well, can we use the Earth? Can we reasonably infer the composition of the Earth given just its mass and its radius? So to do this, we have to solve three equations simultaneously. Let's see if I can. Pointer is weird. Okay, so the first one is the mass within a sphere. The second one is hydrostatic equilibrium, and the third is what I predominantly use BurnMan for, which is to solve the equation of state. I'm using only isothermal, and this is because I have expanded BurnMan to include iron. So I added my own mineral of iron to solve for the density of the core as a function of depth. And so the first model we ran was just a simple two-layer planet with a solid iron core, and you can see the black dashed line here is Prem, the blue line is the output from BurnMan. A solid iron core with a bridgemanite mantle, so not even an upper mantle, and you can see sort of the density deficit right there, as well as the pressure profile throughout. And this actually produces a planet, this simple two-layer model, with the core pinned at the known core radius. You would estimate an Earth that is about 13% too big. And that's mainly because the core is too dense, which is something we've known that our core is more dense than, or is less dense than solid iron. So you actually need to account for some amount of light elements in the core. So we actually, without assuming light elements in the core, we wanted to change as many compositional variables as we can to see how that affects mass, as well as a geochemical parameter, which is, in this case, we chose a major element ratio, silicon over iron, which is kind of as a very loose measure of mantle to core ratio. The bigger your mantle is, the more silicon you'll have. So SI over FE should be high, and vice versa, the smaller, and vice versa. So I'll zoom in on this plot so you can actually see everything. And this is changes in blue are changes in the mantle. So you can see how mass changes as you add iron to the mantle by, let me get the pointer again. Decreasing the mantle magnesium number will increase mass while not really changing SI over FE that much. Whereas this downward pointing blue line is changing the magnesium silicon number of the mantle, as well as changes in the core, which we've got the actual core size. Let's not even assume that the core is the radius that it is, and expand it or decrease it, changing core density, as we said. And then I've plotted here in the red the sun and the Earth. So if we were to, using this model, we would sort of be able to backtrack. We could learn a little bit about the interior structure of the Earth from this plot. Now, I'm not going to show it here, but if you actually include the upper mantle in this calculation, you actually get fairly close to a chondritic Earth magnesium silicon, as well as a core density of about 90% of pure iron. So from this simple turning compositional knobs, you can actually learn quite a bit about Earth structure just from its mass and its radius, and knowing a little bit about its chemistry. Oops, too much. So that's how I'm using BurnMan to apply to my studies of exoplanets. Okay. Timo, were you going to talk about the future?
Yeah, I think so. So going forward, we're going to continue to use this for our projects and to extend BurnMan. We are going to meet up at the end of the year around AGU, and the hope is that we can clean up a lot of the structure and the objects and the code inside the library. We are trying to do inversion, and there it actually matters to have very good performance. So we're working on improving the performance. There's smaller stuff like Python 3 compatibility. Right now you have to use Python 2, and a lot of other stuff that is coming. And so we're planning to do a release at the end of the year with all these new things. And long term, we are planning to. This is part of this is coming. A lot of this is coming from Bob. Is to do Gibbs-free energy minimization. So that you actually compute the phases that the materials will be in, based on energy computation. The next thing is that that is what I envision, is that we manage the coupling with the mantle convection code aspect. So the idea would be you pick your mineral physical data, push a button, and then you can do 3D mantle convection simulations with this material model, with this input. That would be really cool to have. And Sanne mentioned this earlier already. We were talking about putting in 3D seismic models, and that we can compare with those. And I guess a lot of other stuff, but that's what we have on the list so far. Okay, so this is the last slide of the presentation that we prepared. We would like to thank, well, you as the listener, everybody who helped with the talk right now, Lorraine, Cider, CIG, thanks for the hosting, and you can find more information. This is the paper that got published about BurnMan. We have the website, which is on the first slide, hosted at CIG. We also have burnman.org, and you can find a manual there, PDF manual. You can find all the examples and all the code that you can use.
Tutorial as well.
Yeah, the tutorial as well that we probably don't have time to talk about, but so I would like to maybe open it up for questions now, if there are any.
Great, thank you. And yes, and thanks to our audience as well as to our presenters today. We appreciate everybody's effort, and especially all those who are in different time zones and stayed a little later for this. So we are open for questions. If you have a question, please raise your hand or type in the chat box. If not, maybe we'll have a little bit of time if you want to show us the tutorial or where they can find some of these materials. That could also be good. I have one question is, what advice, after going through this project, what advice would you give anyone who is interested in starting an open source software project like this? Are there any lessons learned from this collaboration or any sort of just general good software practices that you found you need to put in place to make this collaborative work?
Sure. How many hours do we have to answer this question?
Well, it depends how many questions everybody else has. But anything you found that kind of particularly stuck, that that struck you?
Python. None of us knew Python, so that's a good practice.
Yeah.
Start with the scripting code in there. Nobody knows.
Yeah, I think we did a lot of things right from the start. Python is a language that's easy to use, and I think that was important that others can write an example program in 5 lines of code that does something useful. Yeah.
I think it also really helped a lot that we got funding from Cider to meet up at times and have, because most of the work got done over a couple days when we were actually in one place. And so those were really useful meetings. So meeting up once or twice a year has been very crucial.
And Ian mentions unit testing.
Yep.
It was very important to keep on checking your code as you progressed. Make sure you catch errors early on.
Yes, and Timo taught us good coding practices.
Yeah.
My other codes look a lot better now too, and I pay attention to certain things.
Great.
Yeah, I have to say working on this project has just made me a better coder. Yeah, because the scale of this project, while the mineral physics may be simple, the scale is much bigger than you would expect. So having it all work together and being modular especially was definitely very useful, especially as I hopefully write more open source software.
Yeah, I think when you're coding with other people or coding for an audience, it makes you a better coder and more mindful of your practices. So while we're waiting, I just want to make a couple announcements. Our next webinar will be next Thursday, November the 12th, and it will feature Anders Peterson from LLNL, who will introduce us to the wave propagation code SW4. As always, more information on all these events can be found on our website at geodynamics.org. And if there's anything you want to go back to, I will, with permission of the authors, post the slide, and we'll be posting the video probably in about a week. Last chance. Okay, thank you once again, Timo, Sanne, Ian, and Cayman.
Thank you.
Thanks.
Well, thanks everyone.